Good afternoon, everyone. This is the numerical investigation of the effects of CO2 and CO2-O₂ co-exposure and their effects on the Class H cement and downwell conditions. The experimental part of the work was just presented by my colleague Chang, and I will go to an interface that we developed for the numerical modeling. CO2 is the most important factor in the global warming. Therefore, we need to capture the high amount of CO2 from the atmosphere and put that in a safe place. And one of the best options for this seems to be the CO2 sequestration. But the problem with CO2 sequestration is the CO2 leakage. And one of the weakest points for the CO2 leakage seems to be the wellbore system itself. In this figure, as it was again shown before, the wellbore cross-section is shown, and there are different possible pathways for the CO2 leakage. So even with the completely perfect system, we have the degradation of the cement, which is the concentration of the current research. For the purpose of reactive transport process during the degradation of the cement, we developed a Java interface which connects two software. One COMSOL Multiphysics, which is a finite element software and has a Java API interface, and the other is the GEMS PSI, which is the thermodynamic, which includes the thermodynamic and does the geochemical modeling. We connect these two software through the diagram that is schematically shown here. And also for accounting for the degradation of cement-based materials, we needed a thermodynamic database covering a high range of temperatures. We used SEM data 2014 from the MPA group, which covers the range of temperatures to 100 degrees centigrade. So I'm going to show the responsibilities of two different software we used. First, the finite element software, which is used for the transport part. The mass balance equations are developed in COMSOL for 12 different atoms that we have in the system. Actually, we have more types of atoms as well as we have from the lab data, but these are the major ones. We apply the transport equation. On the right side of the flow, you see the gradient of diffusion, electrical migration, chemical activity, and the last part is advection, which itself includes the gases and aqueous advection parts based on the pressure gradient that we might have in the system. Also, the potential of the system is found through a Poisson's equation that relates the potential of the system to the valence number and the aqueous form concentrations. This is the responsibility of the transport part, and the responsibility of the reaction part, or GEMS PSI here, would be two main parts. The first part is the cement hydration. As was explained before, the cement are put after 1 day age in the autoclave. It means that they are not fully hydrated. So the hydration is going on. So we need to apply the hydration in our model. The figure here in bottom shows how different cement phases are dissolving into water, and GEMS gives us the result of the reaction as the production of hydration. Cement has generally 4 main phases, including C3S, C2S, C4AF, and C3A. And this special type of cement that we use has very low amount of C3A, which results in very low hydration rate and very low amount of cracks, which is very suitable for the wellbore system. And the result of hydration would be calcium silica hydrate, which we call it CSH after this, and the cement chemistry, portlandite, ettringite, monosulfate, and some other phases which are not major. In the figure, we have a log scale. We have a log scale at the horizontal axis showing time, and different solid phases are dissolving, and different productions are seen here. The second responsibility of GEMS is the carbonation, which is occurring simultaneously with hydration. On the left figure, we see cylindrical sample, cylindrical sample which is put in the brine, and it's a part of its cross section, which is put near the brine, and this is the surface of the sample. After some time, we see three clear carbonation zones. Zone 1 is actually the zone when portlandite start dissolving. Zone 2 is where portlandite has depleted, and we have precipitation of calcite. Calcite has a bigger molar volume compared to portlandite, so we have a smaller porosity in zone 2. And zone 3 is where the calcium has completely depleted in a solid phase, and we have just amorphous silica left. So the alteration depth that was reported in the experimental plan is the sum of the depth of these three zones. And also a picture in the right shows these three zones on the prism sample. We used prism samples in this experimental plan because we wanted to have some mechanical results, and we needed to have prism samples. So we put these two software together in an operator splitting technique, and we start modeling what we have in our project. The whole story of project is summarized in these figures. We cast the sample, wait for 1 day for it for a little bit hardened, and after that we put sample in the brine and make pressure up to 300 bars and temperature up to 85 degrees C, and make a one-dimensional model from a cross-section of the sample as it's shown in this figure, and make a discretization based on the geometry on the sample and finite element software. So all the results, in all the results, the left node of the one-dimensional sample will show the sample center, and the right node is the node where sample is exposed to the brine. Based on all this story, we have 4 cases we want to see how the Java interface works. The first case is nothing to do with the experimental part. It has a basic analysis showing how carbonation zones are forming. The case 2 and case 3 are CO2 exposures and high temperatures, and also high temperatures, high pressures. And in case 4, we apply the 4% of oxygen with CO2 exposures in our analysis. So first I'm going to show the results of the first case. Here we have 1 bar pressure. I just used the PSI units. It would be about 15 PSI and 23 degrees C. Here the carbonation zones are completely clear in the left figure. In all of the figures, the left node shows the sample center, the right node shows the sample surface. And we can see 3 different zones of carbonation here. Here we have zone 1, and zone 2 is where we see the calcite precipitating. We have smaller porosity in zone 2. And after that, in zone 3, where we have fully hydrated, fully carbonated cement, we see just amorphous silica left. And the C/S ratio, which is calcium over silica ratio, and the solid phase completely goes down to 0 in a fully carbonated place. If we take a look at how calcium ion is changing, we see a negative slope, which is showing the calcium leaching out from the surface of the sample. And also the pH of the system is going down. For the cases where we don't have calcium in the brine, the pH is going down up to the level of 4. But for the brine that we use in the experimental plan, we see higher amount of pH. So after that, we go to the case 2. Case 2, we use the Mount Simon brine. The composition was explained in the previous presentation. And this is the evolution of carbonation depth during time. So the case 2 is just based on high temperatures. After just 0 day, just as at start, we have a very small carbonation rate because we have some small amounts of carbon in the Mount Simon brine. But after 14 days of exposure, it changes to 0.05 millimeter, and we can go further up to other levels. You see that the amount of calcite is going higher and higher, and finally the depth of carbonation is going about 0.2 millimeter at 42 days. In the case 3, we apply the same story, but with high pressures. We change the pressures in 6 hours to 4,200 psi. Again, and here at first, we have very small carbonation depth based on the very small amount of carbon we had in Mount Simon brine. And after 14 days, it changes to 0.2 millimeters. Here we see very uniform amount of calcite forming in high pressures, but it changes to 0 at the surface of the sample. It's not completely shown in these figures. And up to 42 days, we see a carbonation depth be much bigger. And this yellow one shows the results of the experimental plan, which is completely comparable with what we have found in the numerical modeling. Actually, the result is very sensitive to what we have to the porosity that we apply to the system. We found, after 42 days, we found the depth of alteration about 1.3 millimeters. After all these 3 cases, we wanted to see if secondary minerals are precipitating or not, so we applied a combination of CO2 and 4% of O2 in 4,200 psi and 85 C. So the alteration depth that we found is smaller than what is found in the experimental plan. In the experimental plan, it was found about 0.6 millimeters with the high variability. It's about it's twice this amount, which seems that the porosity that we have applied to the system might be different from those that was exactly in the experimental part. Also, the pH of the system is going down to the level of 4, and as it's seen in the figure, these small amounts of solid minerals are completely dissolved after carbon starts coming in. So in the numerical work, we didn't see any amount of secondary minerals. As a conclusion, we generally have comparable results with what we had in the experimental plan, but the results are very sensitive to the porosity, especially to the porosity. And different carbonation zones, we could see different carbonation zones from our different results, and we didn't see second minerals based on the thermodynamic database that we have just used until now. For the future research, we want to go to a 3-dimensional domain and apply more efficient methods of numerical technique based on more accurate iteration technique between 2 softwares. And also, one of the main problems in the experimental part was corrosion. So corrosion of well casing is one of the most important things that we want to go in the future. Thank you very finally, we should acknowledge the great support by the National Energy Technology Lab from Albany, who supported this project during the last year. Thank you very much, and I'll be happy to answer any questions.
Are there questions for the speaker? We've got some time. I have oh, well, I see a hand coming up, but.
Yeah. Question. So this is a question for both you and the previous speaker. So the net take-home message is that if you add oxygen to the CO2 stream, it's going to have no impact on the alteration of the cement.
Can you repeat that question?
The question, as I understood what your question was, that the oxygen has no impact on the alteration depth.
Is that what I'm to take from your interpretation?
You know, what we see from the numerical results are completely related to the thermodynamic database that we use. So, and in the numerical part, we just concentrated on the ettringite and monosulfite to see if there's any expanding amount of ettringite or monosulfite. We didn't see ettringite and monosulfate, and the experimental part also didn't see any ettringite monosulfate expanding amount of these 2 minerals. But in the experimental part, there were some small amount of other minerals that are unknown, and being more familiar with these needs more time and research, and staying for more time, because we just waited, these results are just after 14 days. So the amount of time that we are reporting all of these results is very short. We can't conclude right now, and the research is under progress.
What would happen in conditions where there is no water actually in the sediment? Due to the fact that you inject CO2, for example, to penetrate the
Could you please repeat the question?
what happens when there is no water in the cement, in contact with the cement?
Just water?
What happens
There is
when
no
there,
water.
when there is no water, if the CO2 dehydrates the system and removes the aqueous phase?
Oh, you mean the supercritical CO2 in high pressures? That's the case where we don't have water. You mean instead of brine what happens if we have just water or just CO2?
Just CO2.
Just CO2.
Just this case is actually the case that happens when we have high pressures. We turn the pressures up to 300 bars, and one approximation in the numerical part is that after about 80 megapascals, CO2 turns to a supercritical immiscible phase. So it has a high viscosity. It surrounds the sample, and the brine goes a little bit far away from sample. So your question is actually what is happening in high pressures, and we are still going through that, because if we want to model that, we should apply another domain just based on the supercritical CO2. What we think is that the transport of species would be the same, but the depth of alteration would be much higher. You see that we see small alteration depths compared to experimental results. If we change that to supercritical CO2 phase, I think it would be higher, because we have advection in our study.
Oh, one more question?
So initially you show you link your transport code with the mechanical to a Java interface. Why do you do that? How do you use your mechanical code?
You mean how did I develop?
I mean, you have a mechanical part, right? You link your transport code with a mechanical code to an interface in the second slide.
Okay, I can go. Do you have time?
Yeah, this part. Oh, okay.
The COMSOL multi. Okay. The COMSOL multiphysics is a finite element software. We just use it for the transport part. We do nothing for the mechanical part.
Okay.
We just apply that for the transport equation, and they are solved as hyperbolic equation in the 1D domain.
Okay. All right, one quick question.
Did you have a constant diffusivity all through the samples, or did you vary swing velocities?
Could you please repeat?
In your equations, it seems like
Yeah.
is your diffusivity constant for each of the layers, or do you change?
The diffusion coefficient is variable. It's temperature dependent, and also it's dependent to the tortuosity of the system and also the saturation degree of the system. It's not been shown here.
So what was the tortuosity?
We related all of them to the saturation degree of the system. Tortuosity has an empirical relation with the saturation degree, and saturation degree is related to the pressure gradient in the two-phase flow. So we applied all those equations. Tortuosity has an empirical relation with saturation degree.
But what about change in porosity?
We applied porosity based on, we have a reaction part. At one step of the analysis, we find the result of, for example, hydration or carbonation, and the solid phases have different volumes. So the porosity is changing based on the precipitation and dissolution of different solid phases. It means that porosity is time dependent and space dependent. And after that, the tortuosity is changing. The saturation degree can change, and all of the other related parameters can change.